Hi everyone, this lesson is on combinations from probability chapter. So let's get started. We're going to start with a little warm up, and the last lesson we learned about permutations, and so we're going to continue that and just do a little warm up for that. And we have 9 permutations of 4, and so that one way to think of that is to say, well, using the formula, we have 9 factorial over and then 9 minus 4 factorial. And so that would equal 9 factorial over 5 factorial. And then we could reduce that 9 times 8 times 7 times 6 times 5 factorial. And then those 5 factorials are going to cancel. And then my answer would just be whatever 9 times 8 times 7 times 6 is. And, you know, whatever that is. I could do that on my calculator. Let's see what that is. Let's see. 9 times 8. 7, 6, 5. Nope, not 5. 5 got canceled. And, okay. I'll try that again. 9 times 8 times 7 times 6. And I get 3,024. So 3024. Another option is to do it this way, where you have 1, 2, 3, 4. So you've got 4 of these, and so you've got 4 places, and it's just 9 options on the first try, then 8, then 7, then 6, and then that's it. And you would just still multiply those 4 numbers out. In how many ways can the letters in banana be rewritten where order matters? So what the problem is here is that the letters in banana, some of them repeat. And so we have 1, 2, 3, 6 letters. So that's 6 factorial. And then we're going to put our repeaters underneath. So we have 3 A's. So we have 3 A's. And then it looks like we have 2 N's. So 2 N's. And so that would be dividing 6 factorial divided by 3 factorial and then 2 factorial. So that would equal 6 times 5. Oops. Sorry about that. 6 times 5 times 4 times 3 times 2 times 1 all over 3 times 2 times 1 times 2 times 1. And so that's representing all the factorials written out. I'm going to divide out the 3, 2, 1, and those are gone. Then I have 2 times 1, I'm going to divide out with the 4, so that's 2. So what I have here is 30 times 2, so there are 60 different ways that the letters in banana, distinguishable ways, can be rewritten. And lastly, how many ways can you arrange a 12-volume set of books on your bookshelf? Well, if I'm not given any specific spaces, like you have only 3 spaces or something like that, then it would just be 12 factorial. But if I change the problem and I said, hey, I only want to choose 3 books out of the 12, but how many different ways can I do that? That would be 12 permutations of 3. So that would be 12 options the first time. Then I would have 3 options, and next I would have 11 because I used 1 book, and then the next value I would have 10 because I used 2 other books. And those books, once you use them, you're not going to replace them because you've already used them on the shelf. They're on the shelf already. So today is all about calculating combinations as opposed to permutations, where permutations, order matters. Combinations, order doesn't matter. And we have one of my really favorite slides is this one right here. It really shows you the difference between a combination and a permutation. So for example, just looking at, I know this is a lot of writing, but if you just actually look at this first line, ABC, how many different ways can I rewrite ABC if order matters? If order doesn't matter, there they are, ABC. I've got all the letters, ABC. But if order does matter, then I could rewrite just the letters of ABC 1, 2, 3, 4, 5, 6 times. That's 3 factorial, okay? And so depending on if order matters or not, you're going to have so many more permutations than you are combinations. Because combinations are just, I want everybody to come, etc. Permutations are people have to come in a certain order, that kind of thing. So just I love this slide just because it really shows you all the different ways. Like if I have the letters B, C, E, combinations, there they are. I've got all three letters. Permutations, well, I want a B first, then C, then E. No, I want a C first, then E, then B. No, I want an E first, then B, then C. So definitely permutations where order matters are going to give you a lot more ways than a combination. So again, permutations, order matters. Combinations, order doesn't matter. And so we do have a combination formula for this. You're just choosing these people. So you've got combinations, you've got the number of items in a set and the number of items that you're selecting. You're choosing R. That's how much you want. R is what you want. So there's lots of different ways, and different textbooks use different ways to write, the actual presentation. Also, another way is writing it N over R, like that. And we're going to talk about that in a minute. But the rule is similar to a permutation where you have the N factorial over the N minus R factorial, but you're also multiplying by the R factorial. So that's going to reduce the number because you're dividing out, the number that you want, not just the number you total divided by the number minus what you want, but you're also dividing out the value that you're seeking, okay? So two formulas, again, this is another way, I know in college this is how I saw it. Different ways, different books, okay? So basically what this all means is we're going to pick a number, like let's say I have 5 books and I only want to bring 3 with me. So I'm going to choose, and it doesn't matter, I don't care which ones I bring. I'm just going to choose 3. So that would look like this, 5 factorial over, you'd say 5 minus 3 factorial, and then it would be 3 factorial. So you're rewriting this value goes here, this value goes here, and then right here, this 5 minus 3 is the difference of the two. So we would have 5 times 4 times 3 times 2 times 1 over 5 minus 3, which is 2 factorial. This one right here is 2 factorial. So 2 times 1, and then my 3 factorial, which is going to be 3 times 2 times 1. So my 3 times 2 times 1 are going to cancel. 2 is going to divide into the 4 twice, and so 5 times 2 is 10. And so I have 10 different ways that I can select n objects are at a time. So n objects are at a time. Okay. Whereas at a permutation, right, I would just have 5 factorial over 5 minus 3 factorial. And if the order mattered in the textbook, like the books that I wanted, the order mattered, then, I'm going to have a lot more ways that I could, bring the 3 books. So just simplifying these 3 problems here, again, this is the same thing as saying 7 combinations of 2. And so that would be 7 factorial over 7 minus 2 factorial, which is 5 factorial, and then 2 factorial. So again, 7 times 6 times 5 factorial. 5 factorial is going to cancel with this 5 factorial. And then I have 2 times 1. 2 is going to cancel with 6 3 times. 7 times 3, 21, last time I checked. And so let's do that. Box that up. For this one here, we have, again, 6 factorial over 6 minus 4, which is 2 factorial, and then 4 factorial. And so that 6 times 5 times 4 factorial cancels with this 4 factorial. I still have 2 times 1. 2 is going to cancel with the 6, leaving me 3. 3 times 5, 15. For this one, I've got n factorial over, and then I'm going to rewrite this one here, n minus 1 factorial. That's just the rewritten part, like this 4 is that 4. This 2 is that 2. So that n minus 1 is this n minus 1. But then in here, I have to subtract. So I'm going to go n minus the quantity n minus 1. And so that will make factorial. And that will make a difference because I'm subtracting. So we've got n minus n, and then plus 1. N minus n is gone, so I have 1 factorial, which is just 1. So this is gone. So n factorial is n times n minus 1 times n minus 2, and this is going to keep going factorial. On the denominator, I have n minus 1 factorial. So n minus 1, start with the value that you have, n minus 1, then you're going to decrease it, n minus 2, and then n minus 3, etc., and that's factorial. So what realistically happens is these n minus 1s, n minus 2s all become 1, and they cancel out all the way down the road, and you just end up with your answer being n. Which is bigger? Combinations, permutations. We have 5 permutations of 3. We have 5 combinations of 3. So permutations, we go 5 factorial. So this would be 5 permutations of 3. So we have 5 factorial over 5 minus 3 factorial, which is 2 factorial. So that's going to be 5 times 4 times 3 times 2 times 1, which is 120, divided by 2. Factorials are gone. We have 20 times 3, which is 60. So this is going to give me 60. Whereas if I have the combinations, I have 5 factorial, which is 120, over 5 minus 3, which is 2 factorial, and then 3 factorial. So what I have is basically 5 factorial, which is 120, divided by 2 factorial, which is going to leave me 60. So I have 60 over 3 times 2 times 1, which is 6. 60 divided by 6 gives me 10. And so 10 combinations versus, and this is my 5 combinations of 3. So I have permutations here, combinations here, 10 combinations where order doesn't matter. I'm bringing all 10 of it. Or, you know, permutations where order matters. I want everything in a certain order, okay? So a couple of interesting things here that we're going to see. When I have a 3 permutations of 3, let's see what happens. 3 permutations of 3. So that's going to be 3 factorial over 3 minus 3 factorial. 3 minus 3 is 0 factorial. 0 factorial is 1. 0 factorial is 1. And so equals 1. And so 3 factorial is 3 times 2 times 1, which is 6. 6 over 1, 6. So 3 permutations of 3 gives me 6. 4 permutations of 4. So let's do that. I'm having some issues with this. 4 factorial over 4 minus 4 factorial, again, 0 factorial. So we get 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2, 24, times 1. So this is going to give me 24. N permutations of n. N factorial. Here's our little formula. N minus n factorial. And so hopefully you see that this is a pattern. If I have a permutation with n factorial, if I have a permutation of itself, n permutations of n, my answer will be n factorial. If I have 4 permutations of 4, my answer is 4 factorial. If I have 3 permutations of 3, my answer is 3 factorial. So whatever that value is, it's n factorial. Whereas in a combination, 3 combinations of 3, that's going to give me 3 factorial, 3 minus 3 factorial, which is my 0 factorial, and then this value 3 factorial, 1. 4 combinations of 4, again, 4 factorial over 0 factorial, 4 factorial, 1. N factorial over n minus n factorial, and then n factorial. N's cancel, make 1. N minus n, 0 factorial, which is 1. 1 times 1 is 1. So that's kind of interesting. I like that. Again, just different ways to write the formula. This right here, where that's come from. Multiplying a combination, right, by k factorial will give me the permutation. This I love, because it's like, oh, that I get it. Okay, so let's go to Giordano's Pizza. Oh my gosh, Chicago pizza. If you ever have a chance to get to Chicago, go to the deep dish pizza, Giordano's. Oh, my absolute favorite pizza. I'm Italian. I love pizza. This is my favorite pizza, hands down. Love it. I mean, I also like the thin crust. Yeah, but this is one of my favorite. No, not one of my favorites. It is my favorite. So combinations. So we've got this deep dish pizza. Oh my gosh, I'm hungry now. Select 3 toppings from a list of 20. I don't care which ones I pick. I'm just going to pick 3. I have 20 to choose from. So we're going to have 20 combinations of 3. So that's going to be 20 factorial over 20 minus 3 factorial, right? So let me just write this down one time like this. 20 minus 3 factorial, and then 3 factorial. So we've got, let's see, 20 times 19 times 18 times 17. I think that's all I need, right? Because 20 minus 3 is 17 factorial. The 17 factorials will end up canceling out. And then I get 3 times 2 times 1. 6 is going to go into this 18 3 times. And what's left? I think, do I have this somewhere? Maybe. Let's see here. 20 times 19 times 3. I believe that that's 1140. Okay. Let's see if. All right. 12 people win a raffle to go on the Marvel Starship. I mean, who is that lucky? I don't know. But there's only room in the Starship for 5 of them. So they're just going to randomly choose 5 people. So how many different ways can we choose 5 people out of 12 to go on the Marvel Lego Starship? I mean, what a treat. We've got 12 combinations of 5. So that would just be 12 factorial over 12 minus 5 factorial, which is 7 factorial, and then 5 factorial. So working this out, 12 times 11 times 10 times 9 times 8 times 7 factorial. 7 factorial will cancel with 7 factorial, and then I get 5, 4, 3, and then 2, and then 1. And just a heads up, 5 factorial is 120. You know that 12 times 10, also 120. So those are going to cancel, make 1. So realistically, what I have left is 11 times 9, which is what, 99 times 8. So 99 times 8 is 792. And so, different ways that you can reduce it. Also, your calculator will do this somewhere under probability. Find it. It'll make your life happy. So this is an interesting question. This has to do with the Supreme Court justices. They have this really cool handshaking ritual that they conduct just before each session, where each of the justices shake the other justice's hand. But what you have to remember is that how many handshakes, so how many different combinations? 2 things you have to know. Number 1, how many Supreme Court justices are there at any given moment? 9. And so we have 9 to choose from. So combinations. And this is where it does get a little bit tricky because 2 people have to shake the hands at the same time. So 2. So 9 combinations of 2 people at a time is going to give me 9 factorial over 9 minus 2 factorial, which is 7 factorial, and then 2 factorial. And so let's see, the 7 is going to cancel. So that's what, 9 times 8 times 7 factorial. 7 factorial cancels. I have 2 times 1. 2 is going to cancel with that 8 4 times. 9 times 4 is 36. And what that means is that you have 36 handshakes on any given day, every day, that the Supreme Court justices meet. So very cool. Probably stop during that during COVID, of course, but aside from that, that's a very cool ritual. So let's go back to normal hand decks. So we've got 5 cards of poker, 5 card poker hands. I guess I'm gonna try to get that right. And what you have to think of is like how many cards. Well, we've got 52 cards in a normal set, a deck. I love this picture. Painting, it's actually iconic, but anyway. And how many different 5 card poker hands could be formed? 52 combinations of 5. How many is that? How many can we choose from? We've got 52 factorial. 52 minus 5 factorial is what we're working with. So 52 minus 5 factorial, and then write down the 5 factorial. Work this out. You guys start using your calculator with this. I ended up, I think, getting 2,598,960. And I think what that is, that's how many different combinations of 5 hand poker cards I could get. Bridge is a little bit different because I think bridge, you have 13 cards. It's kind of like playing hearts almost, but not really. I've never played bridge, but I know my mom's on a team, and I know they play, and one time they played with Warren Beatty, which is, wow. And not Warren Beatty, sorry about that, Warren Buffett, who is also on a team that they play bridge. So I thought that was kind of cool. I'm like, whoa, mom. How many different 13 card bridge hands? So that would be 52 combinations of 13. And so many, because you've got 13 cards at a time, right? And so we'd go 52 combination, or 52 factorial, 52 minus 13, 39 factorial, and over 13 factorial. And I think doing this, I don't know, I ended up getting 635 billion, 1, 2, 3, I don't know, something like that. Yeah, a lot of combinations that you could possibly get if you're each given 13 cards. So many. So here we are. We have Eileen and Ben, 2 of the 9 people. If a committee of 5 is selected at random. So this is a little bit different than what we've been doing. Okay, so what we have here is we have Eileen and Ben. We have a committee of 5 being selected from 9 people. Okay, so the 9 people are being split up into 6 women and 3 men. Now, 2 things that are happening. Number 1, I'm going to be choosing some women and some men. Also, I'm asking for the probability. So I'm asking for the entire choice, like how many, so total, if I'm choosing 5 people at random from a set of 9, the total that I could choose is 9 combinations of 5. So that would be 9 combinations of 5. That's like the total. Now, because I'm choosing some men and some women, that's going to change, my outcomes, my probability, and the combinations, of course, that I'm choosing and that I'm selecting. So the first thing I want to do is I want to know what's the probability that I am going to choose Eileen and Ben. They are 2 of the 9 people. So once I choose Eileen and Ben, that's like a 1, that's 1 and 1. Now I have only 7 choices left, right? And so I left this as with the wording on it because I wanted you to see what is actually the textbook is telling you, but I will explain this as I go. Whoops. So what this does is it says, look, we want to select Eileen and Ben. There's only one option for that. One way I can do that. But then after I choose Eileen and Ben, that's 2 people out of the 5 that I actually want. So 2 people out of the 5 leaves me 7 people left to choose from, right? So now I have 7 possible ways, 7 combinations of ways that I can pick the 3 remaining people out of the 5. So there's actually 2 things that are happening, right? So number 1, I'm going to choose Eileen and Ben. So that's one option. Additionally, after I choose Eileen and Ben, that's my one option. And then I'm going to choose 7 people. Out of the 7 that are remaining, I'm going to choose 3. And they're not saying that you have to have men or women. They're just saying pick 3. All right. So that's where the 7 combinations of 3 come in right here. And so 7 combinations of 3 ends up being 35. So that's one part of the problem. The second part of the problem is I'm asking for the probability. And so when I'm asking for the probability, that's going to be 35 out of the total choices that I have. Now the total choices I have was 9 combinations of 5, right? And because that was 9 people to select and I'm choosing 5. And so that was the total. And so when you multiply these out, or, when you do this, you get 35 over, I think I got 126. And you divide those out, the probability is 35 over 126. You guys can reduce that, but it's about, actually, I don't think you can reduce it. It's right there. 28%. So when you divide 35 divided by 126 and change that to a percent, multiply by 100, you're going to get 28%. Okay. Now, the next question says, now, now that I've done that, okay, now erase everything we just did. Now let's just choose 3 women and 2 men. So now this is where you have to ask yourself, all together, I want 5 people, okay, total. Of the 3 women I want, I actually have, if I look up at the top here, I actually have 6 women to choose from. So I have 6 combinations of 3 because I have 6 women to choose from. So that's going to give me my 6 combinations of 3 for the women. For the men, I have 3 men to choose from, but I'm only going to take 2 because it tells me right here, take 2 men. All right, so of those guys, I have 3 men, 3 combinations of 2 because I only have 2 men. Because I'm choosing the women and then the men, and then remember from our counting principles, that's times. So we are going to multiply these 2 together. And I think that gives those values, okay? Yeah. And so what happens here is this is just explaining what I just said. All right, so we have selecting the women. We have 6 women to choose from. We have combinations of 3. So we only are taking 3 women, 2 men. Of the men, we're taking 2 men, but I have 3 men to choose from. Now, additionally, remember that you have to think back as what's the total value. So if you think of it, see this 6 and this 3, that has to add up to 9. Just kind of verify, go backtrack. Also, the 3 and the 2 are what you're choosing. That's what you want. Remember, that's your R value. And those values have to add up to the 5, all right? So basically, we get the values. We do that. I'm going to make that. I think I can make that a little bit bigger so that you can see the math part of it. But this is what we did. We choose 3 women and 2 men. We have 6 combinations of 3 times 3 combinations of 2. Once you do that math, you get 60. So there's 60 ways that I can choose 3 women and 2 men, 60, out of the 6 women and 3 men that I had. Now they want to know, the second part of the question says, what's the probability? So now that's where I take my 60 and I divide by the total possible options, or my sample space, which is 9 combinations of 5. And so 9 combinations of 5, I did that before somewhere, 126. So 60 divided by 126, definitely you can reduce that. Also, that becomes 48% once you divide them out and then multiply. Right? That's kind of cool. This is really a neat way of doing these questions. Okay, so now we're going to do this again. Same problem, but now we have a committee of 5, same selected group of 9 people, but we're going to choose different people. So now instead of just choosing, let's see, how many am I choosing now? Instead of just choosing 3 women, I don't remember, 3 women and 2 men, now I'm actually going to choose from a group of 9. I want 3 women, at least 3 women. So this is where you have to ask yourself, if I want at least 3 women, but I want 5 people total. So that would make 3 women option, right? 3 women. I could have 3 women and 2 men. Okay, that's one option. At least 3 women. I could have 4 women and 1 man, or I could have 5 women and no men, because remember, I only want 5 people, same problem, right? So these are the different options that I have: 3 women and 2 men. I could have, if it says at least, so then 3 is the minimum, 4 women and 1 man, or 5 women and no men. So this is just how you would set it up. I'm just going to open this up for you. You've got all of these different ways. And so when you set this up, you could do 3 women and 2 men, 4 women and 1 man, or 5 women and no men. So as you set this up, right, these are your combinations. So 3 women and 2 men is this option right here. This is this one. 4 women out of 6 and 1 man out of 3 is this option. And then lastly, 5 women and no men is this option right here. So my options, once you do all of that math, and this is they've not shown all the math, right? Because you know you've got, for this, just this one, this blue one right here, I'll use blue. Just for this one, you've got 6 factorial over 6 minus 3 factorial and then 3 factorial times 3 factorial over 3 minus 2 is 1 factorial and then 2 factorial. So this one step right here is this step here. Just that is that. And they said, oh, we did all the math, 20 times 3. This one value here is 60. The red value ends up being 15 times 3. And then the green value here ends up being 6 times 1. So there's a lot of work in, that goes in behind the scenes here that they're not showing. Again, with the green, that would be 6 factorial over 6 minus 5 factorial, which is 1 factorial, and then 5 factorial, times 3 factorial over 3 minus 0 factorial, which is 3 factorial, and then 0 factorial. So basically, this is 1 times 6, because the 5s cancel. But just this part right here, just that one part is that. Okay, so you get all your individual values. That ends up being 6. And you add those up because it's, because it's not an and then. This part is an and then. You want 3 women and then 2 men. But this is where this word comes into play, or. Because I'm not going to have 3 women and 2 men and 4 women and 1 man and 5 women and no men. I'm either going to have 3 women and 2 men, or 4 women and 1 man, or I'm going to have 5 women and no men. So these are my ors. And so the reason why these values in here are plus is because those are my ors. And then the reason why in between those values are times is because that's the whole part where it says 3 women and 2 men. That's your and. So and means time, or means add. So when you put all of that together, you get that super cool thing, right? Okay, Charlie Brown has 13 socks in his drawer. And let's see, 13 socks, so this is the total socks, right? He has 7 blue and 6 green. Okay. He is going to collect 5. What's the probability? Now, number 1, right off the bat, we want to talk about the probability, because I always like to get that out of the way. The probability is based on the total sample space, which is 13 socks out of 5. So I'm going to choose, he's going to choose 13 socks. Out of 13 socks, he's going to collect 5. And by doing this one problem here, he ends up with what? 1, 2, 8, 7, 1287. So that, whoa, what just happened? That is my sample space right there. That's my sample space. And so when I'm looking for, when it says find the probability, that is the total amount. So I always try to do that first and get that out of the way. So now here we go with Charlie Brown, and he's saying, well, I want 2 blue and then I want 3 green at the same time. 2 blue, 3 green. How many ways can I select 5 socks with 2 blue and 3 green? So we would just go, well, Charlie Brown wants 2 blues and he also wants 3 greens. All right. So he would go, well, 2 blues and 3 greens. So that's going to be, let's see, how many blues do I have? It looks like I have 7 blues and it looks like I have 6 greens. Okay. So Charlie Brown is going to say, well, out of the 7 blue, I want 2. So 7 combinations of 2. And then I have, out of green, I have 6 combinations, but I only want 3 for this problem. And so this is what I'm getting. I'm getting 7 factorial over 5 factorial, 2 factorial, times 6 factorial over 3 factorial, 3 factorial. That whole number works out to be I'm not really sure. What does that make? I don't know. I did this somewhere. 420. And so now what they want is the probability of this happening. So the probability of this event happening of 2 blues and 3 greens is going to equal my value 420 over the total sample space, which is 1287. So that's this part right here. Okay. All right. I'm going to move this to the other side now. Yeah. Okay. Guess I should take the value with it. Okay. Now we want to try 3 blue and 2 green. So we're going to go, Charlie Brown he's choosing 3 blues and 2 greens out of. So we've got 3 blues out of 7. So we've got 7 combinations of 3. And also we have choosing 2 out of 6. So that would be 6 combinations of 2. Now to find the probability, I'm going to take that value and put it all over my sample space, which is 1287. And so working all of that out, I think I get 175 over 429, whatever that is. Okay. All right. And so now, lastly, Charlie Brown says, well, what if I want to choose OR? See that? So OR. So what realistically I have is 13 combinations of 5 is my total sample space. And so that's 1287. And then I guess I can go back to this original amount. I think this top amount before I reduced was 525. Oh, don't do that. Was 525. And so over 1287. So if I have this over 1287, I can just add my 2 sums up, which would be 420 plus 525. And I think that is 315. 429. And what is it about? 73%. And that's what I got. Okay. All right. Last question here. We have an ordinary deck of playing cards. We have 4 suits. Okay, you know, you've got spades, you've got diamonds, you've got hearts, you've got clubs. Each 13 cards in each suit. How many games each of 4 players is dealt 13 cards, like hearts, right? This is a good game. At random. What is the probability of each of these hands? So each person each time is going to get 13 cards. Okay, each of the 4 players. So what is the probability of getting exactly 5 spades? So we'll go SP for spades. It looks like we're getting, let's see, 13 cards. So I'm going to get 13 cards. So that would be 13 combinations of 5 spades. But remember, these values have to add up to be like 52. So like this value and this value has to add up to be 52. And then the combinations, like this value here and this value on the right side, my end values here on the right, that has to add up to be 13. So 5 and 8, that's 13. 13 and 39 adds up to be 52. Does that make sense? So you're dealt 13 cards. You want to try to find the probability that you are going to get 5 spades. So that's what this part is, 13 combinations of 5. But you also have to look at what's left, which is the 39 and the 8. So you have 39 cards left if you out of 52. And you're given 13. So that's a 5, and then there's your 8. So working all of that out, I don't remember what I get, but working all of that out, that's going to be my probability. I would probably just put this in my calculator. But remember, if they want probability, that value on top, the 13 combinations of 5 times 39 combinations of 8, that all has to be divided by 52 cards of 13 combinations that I'm passing out to each person. So you're going to multiply, you know, all of this out. I think the book gives you a definition or an answer for the 5 spades of 12% or 12.5%, something like that, about 12.5%. Okay. Exactly 3 clubs. So for this one, I only want 3 clubs, right? So I'm going to only get 3 clubs instead of 5 spades. So think about it like this. So the number of getting 3 clubs is going to equal, so I'm getting 13 cards. I'm choosing 3. And what's left now? Of the 13, I have 39 cards left. So 39 combinations of 10, because 10 plus 3 is 13. And all of this is over 52 combinations of 13. Okay. Exactly 5 spades and 3 clubs. Ooh. So that, again, remember, those values all have to add up. So we've got 5 spades. So we know for 5 spades, we have 13 combinations of 5. And then for 3 clubs, and then we could have 13 combinations of 3. And so my last value is whatever is left. So 13 and 13 is 26. 52 minus 26 is 26, right? And then 5 plus 3 is 8, but that has to add up to 13. So I need another 5 option here. And this is all over 52 combinations of 13. Work that out. All right. And then 5 spades, 3 clubs, and 2 diamonds. Ooh. So that would be 13 combinations of 5. And then we could get 13 combinations of 3 clubs. So that's 5 spades, 3 clubs, and then 2 diamonds. 13 combinations, or excuse me, that's 2 diamonds. That would be, what is that? 26. And what did they say? 2 diamonds. So I've got 13 combinations of 2 diamonds out of altogether, what is that? 52 combinations of 13. I need my calculator. I feel like I'm missing something though. Hold on. 13 and 13, 26 and 13, not 52. So actually we need one more row here, or one more value here, which is another 13, because 4 13s adds up to be 52. That has to add up to 52. 13, 13, 13, 13, and we've got 5, 6, 7, 8, 9, 10. And remember, I'm giving 13 cards, so I still need another 3 right there. So now this is the correct answer. And so this would be the probability of getting a hand that looks like this, which is crazy. All right, so tonight's homework is page 658, last homework assignment in the textbook for quite a while. So good luck on that. Thanks so much for watching. I hope it helped you in some way. And if not, I'll see you in office hours. So have a great rest of your day.